couple of questions concerning the random walk model as applied to the slow interphase mass transfer term. I want you to think about these and send me an email. Don't mix it with your normal class email, but send it separately. And answer each of these three questions as best you can. I'm not going to grade it. I just want to know if you get it or not. If you don't get it, I'll have to give you some more stuff to read. Okay. When we were working on the C term, the slow interphase mass transfer by the random walk model, we said that the total number of random steps n could be taken as 2 times NB or 2 times NF. Why is that true? It is true, but why is it true? The question's not is it true, it's why is this so? Why can we do this? In the same derivation, we estimated the number of forward steps as being equal to the length of the column divided by the average interstitial velocity times the time it takes to do a single forward step. Why is this valid? It's true, but why is it valid physically? And the third question is, why is the size of the random step not equal to the average velocity times the time of a forward step? I'll post these so that you'll have them exactly. Okay, this is where we got to at the end of the last lecture, and it says that the contribution to the HETP from eddy dispersion, from the flow-induced dispersion, I'm going to say that again, the contribution to the HETP from flow-induced dispersion. We've got some constant of proportionality that Giddings called omega sub beta squared. There's no minus sign there. Times the average interstitial velocity times the time it takes for a solute molecule to get out of whatever flow stream it's in and over to a flow stream that has the average velocity. So if down the column direction is that way, and this is one flow stream, and here's the flow stream that has the average velocity, T sub T is the transfer time to get from this flow stream over to that flow stream. So this is what's going to generate the broadening by the flow-induced dispersion process. Now this doesn't really tell us a whole lot, because what is the value of T sub T? And a number of people in emails asked me, where do you get T sub T from? And that's actually the next part of the problem. But there's 3 different ways that people over the years have estimated this transfer time here. And the first person to do it was Van Deemter. And what Van Deemter said was that the time it takes to get from here to here, from the flow stream that you happen to be in to the average flow stream is controlled totally and completely by convection, by the movement of the fluid, the gross convective flow of the gas or the liquid, whatever is the mobile phase. So I'm going to call this the Van Deemter approach. And I'll also call it the classical approach, because it was the earliest. Within about 3 or 4 years, other people said, at low velocity, that doesn't make sense, because at low velocity, diffusion is going to dominate the transfer process. So they took a different approach, and they said, okay, let's see what happens if this transfer is controlled completely by diffusion. Now, that also is clearly an approximation, because there could be some convective assistance going on. But if we take it to be controlled completely by diffusion, I'll just call this the diffusion model. Then in the late 1950s, Giddings said, well, there's a pretty simple way to deal with both of these transport processes happening simultaneously. That is, he allowed the two kinds of transport to be coupled to one another. And this is called the Giddings model, or the coupling model. Since this is the more complicated one, we'll do it last. So the first model is T sub T is controlled completely by convection. If it's controlled completely by convection, you better not see a diffusion coefficient, right? So here's what they said. Here's what Van Deemter said effectively. This transport time is equal to some constant of proportionality times the particle size. This represents the distance that the two flow streams are separated by. And then it's dominated by convection, so we're going to say that scales with or is proportional to the average interstitial velocity. So that then the transport time is equal to some proportionality constant times the particle size divided by the interstitial velocity of the moving fluid, of the mobile phase, a gas or liquid or whatever it is. Then we take this and we plug it into the equation that we derived by the random walk model for the HETP. So we're going to take that and put it in there. Now, at this point, you can see if I make this substitution, this velocity here is going to cancel with this velocity here. And I'm going to come up with a result that doesn't depend on velocity, because it canceled out. They compensated one another. So when I combine all the constants of proportionality, I come up with an HETP that's equal to some constant, which I don't know the value of. I'm going to have to get it empirically. But the HETP is proportional to the particle diameter, to the first power. So what this is, if you double the particle diameter, the HETP for this term will double. Now, Van Deemter didn't exactly derive it the same way, but he came up with an equation which he wrote as H equals 2 times some constant of proportionality lambda times the particle size. So clearly lambda over 2 is going to be equal to, it's going to be, there's no dp there. Lambda over 2 is this bunch of constants according to the Giddings approach. But the point is that H is simply proportional to the first power of the particle diameter for the flow-induced or eddy dispersion process. If Van Deemter's assumption that transport is controlled only by convection is true. Let's move on to the second approach, where we assume that the transport time is controlled only by diffusion. Now, if the transport time is controlled only by diffusion, the velocity of the mobile phase better not occur in the equation, and the diffusion coefficient better come somewhere. When we were talking about diffusion, we learned that the diffusion, the square of the diffusion distance is proportional to 2 times the diffusion coefficient times time. So we say that the diffusion distance is proportional to the particle diameter. We don't know the proportionality constant, but this thing in parentheses says units of distance. So we have to square it and divide it by the diffusion coefficient, and we throw in the 2 for sigma squared equals 2 dt, and this gives us an estimate of the transport time it would take to move from one flow stream to the other only by diffusion. So then we take this and we plug it into the eddy dispersion equation for the HETP. So we're going to take that and put it in there. So I'm going to have a mess of constants all put together. And now I have the particle diameter squared times the velocity to the first power divided by the diffusion coefficient. And so it's saying that the contribution to eddy dispersion, if diffusion is the sole transport process between flow streams, goes with the square of the particle diameter. This obviously disagrees radically with the first model, which says it goes only with the first power of the particle diameter. It says that it gets worse the higher the flow velocity, which also radically disagrees with the first model, which says it's independent of the velocity. And this says that it depends inversely on the diffusion coefficient of the molecule that's diffusing, which also disagrees with the first model. They couldn't be more different. And this business here looks an awful lot like what we derived when we did the C term. In fact, it's not really very different from the C term. And if this were the dominant mechanism of mass transfer between flow streams, you would have a hard time telling the difference between this and simple interphase mass transfer. So we lump all that stuff together, and so we say that this H, this contribution, is proportional to that collection of terms. Now, Giddings then came along maybe another 2 or 3 years after the diffusion model was put out, and he said, both of these things are going on simultaneously. What that means is that there's 2 parallel paths or mechanisms by which a molecule can get from flow stream 1 to the average flow stream. It can be convected there, it can be pushed by the fluid flow, or it can get there by diffusion. They're parallel paths. So what he did was to add together this result and this result, the way you add together parallel resistors in an electric circuit. Parallel resistors are parallel paths. So here's path 1, and I've changed the constants of proportionality to just make this less cumbersome. So this is mechanism 1, this is mechanism 2, and I'm going to combine them so the total resistance of two resistors in parallel, 1 over R total, is equal 1 over R1 plus 1 over R2. So that gives you this. Now even this is a bit messy to write. So a little while later, when John Knox had invented the reduced parameters, you can apply the reduced parameters I'll remind you of the definitions. To that last equation, here's the parallel combination, and if we multiply it out, there's the equation for the coupling or Giddings theory in reduced parameters. So this is a constant, this is a constant, this is a constant. So this has the form A nu over B plus nu. Well, if you look at this form, at very, very, very low velocity, where nu is less than b, it says that H total is simply proportional to the velocity. So that's the low velocity limit of the coupling equation. And the high velocity limit, where nu is way bigger than b, we have A nu divided by nu, so that's just A. So that's a constant. So the high velocity limit is just a constant independent of velocity. If I plot that up, that's the coupling theory there. Low velocity, it's proportional, it curves over, and then it eventually becomes flat. Here's the classical theory, the Van Deemter. Just a flat line. And here's the diffusion theory, or the diffusion model. Turns out that Giddings does a pretty good job of fitting the real data. Not great job. It seems to work better for gas chromatography than for liquid chromatography. And we'll address specific equations for liquid chromatography a bit later on. So I have to bring back into play again the reduced parameters, right? To make the equations look nice and simple. The reduced velocity is not an arbitrary thing. There are other ways I could combine things so that I would get something that was dimensionless. There is a logic to the meaning of the reduced velocity, and I want to take you through that logic so you get some physical appreciation for what a large value of nu means and what a small value of nu means. Suppose we want to calculate the time for transport on the order of a particle diameter. That diffusion time is going to be on the order of the particle size squared divided by the diffusion coefficient. Length squared over length squared per unit time. That gives us an estimate of how long it will take for something to diffuse a distance dp. The time it takes for something to move by convection over a distance dp is dp divided by the average interstitial velocity. If we take the ratio of the transport time by diffusion to the transport time by convection, so I plug this in here, I plug that in there. This is going to cancel one of those. This UE here is going to come up to the numerator. Lo and behold, nu is the ratio of transport times by diffusion to transport times by convection. That's its fundamental meaning. So, when nu is small, transport is mainly due to diffusion. In other words, transport is controlled by diffusion. When nu is large, transport is controlled by convection. Think about the plot of h, oh sorry, let me do h, little h versus nu, the Van Meter plot, it's like that. When nu is small, the b term is the dominant contribution. The b over nu term is the dominant contribution. You're over here. Diffusion is dominating transport. So the b term is going to dominate. When you're at high reduced velocity, you're over here. This term has effectively dropped away, and your dominant term is your c term. So when you're over here at high reduced velocity, transport is being dominated by convection. So low nu, diffusive transport predominantly, high nu, convective transport predominantly. That's why this is so helpful, and why you don't have to memorize very many values of it to know where the minimum is. Okay, let me move on to the next subject. But before I do that, I want to pose to you another problem. In a couple of days, you're going to, well, in a day or so, you're going to get involved in mass conservation equations. So I want you to work out a very simple mass conservation equation. Here's a cell, a volume. Think of it as a beaker. And you got flow in, and you got flow out. And you got some way to mix what's ever in there. And the volume of this is let's call it V naught. And the cell is going to be completely full of some liquid, let's say a liquid. And the flow in is going to be F, and this will be volume per unit time. And the flow out will be the same thing. You're going to start the beaker at a concentration of some compound A, C0A, Ca, at time equal to 0 is going to be C0A. You can assume that the mixing is instantaneous. So whatever, even though you've got flow in and flow out, whatever is in the cell is always homogeneous. Okay? Do a mass balance on this cell. And then derive an equation for the concentration of A as a function of time in the cell. You know how much A there is in the cell to begin with. There's C0 times V0. That's what's there to start with. But as you flow in and flow out, you're not bringing in any new A, but when you flow out, the composition of the effluent is whatever's inside the beaker, Ca, and is leaving at a rate Ca times F. So set up the defining differential equation and work it out. It's not hard. You have done this problem before if you've taken an undergraduate physical chemistry course, except you call this a reaction instead of a flush out problem. I want you to write it up, scan it, and attach it to an email and send it to me. Again, I'm not going to grade it. I'm going to make sure that you know how to do it. Because you're going to have to do problems like this or see problems like this in class, and you need to understand this one. Okay. Today we're actually going to start talking about or begin to start talking about real chromatography. And in particular, we're going to talk about what goes on inside of what's called a capillary chromatography column. And the reason I start with capillaries is not a historical reason, it's a reason of simplicity. It's much easier to understand what goes on inside of an open tube than it is to understand what goes on inside of a packed bed. Historically, capillary columns came along a fair bit after we were already doing gas chromatography and liquid chromatography with packed beds. This is a conventional packed bed column. There's a tag on it that gives a lot of information about what's in the column. If you look in this end without the yellow thing, you'll see some stuff. That stuff is actually a little bit of glass wool that keeps the particles that are packed in the column so that when you turn it over, they don't spill out. Okay, you don't want, it won't hurt you, but you don't want to lose them. That's the way gas chromatography started, with that type of column. That happens to be a 6-foot long column. The ID of the column, I believe, is a 1/16 of an inch. The OD is an 1/8 of an inch. About 1957 or so, M.J.E. Golay invented the capillary column. This is a stainless steel capillary. The wall of this tube is coated with a stationary phase. It's not filled with particles. It's simply the interior wall of the capillary has a very, very thin film of stationary phase that's on it. And the state-of-the-art advanced from this metal tube, but the metal tube has the advantage of not being terribly breakable, but it's heavy. And it was really hard to do good temperature programming because it's so massive that you just couldn't get a lot of heat into it real quickly was one issue. And stainless steel is chemically sounds inert, but it is not really inert. when it's heated up to, say, 300 degrees centigrade, and you're injecting, nice fragile organic compounds, if they get to the surface of the stainless steel, they're toast, literally. Okay, you don't want that to happen. So the next stage of development was they went from stainless steel to glass capillaries. Now glass is much more inert than stainless steel. It's lighter than stainless steel, but if you touch it wrong, it's a broken capillary, and you're out a lot of work and a lot of money. In the late 1970s, after fiber optic cables were invented, a fellow who happened to work at then Hewlett-Packard Company, his name was Ray Vandenow, said, I think I can take that technology and make fused silica capillaries out of it. And that's what he did. And this is a fused silica chromatography column. And I still remember the first day I saw one of these, I said, this is going to change gas chromatography. This is what you can do to it. It's extremely robust. Compared to glass, it's forever. I mean, you can break it if you hit it with a hammer, but you have to do something like that, or close it in a drawer and close the drawer on top of it. But these are wonderful devices. This is a little bit wider diameter capillary than that one, and it's been deliberately broken so that we could look at the end of it and see what it looks like. The brown stuff on the outside is a polymer coating, which sort of makes the fused silica a little bit more mechanically stable. But you don't do the chromatography on the outside of the tube, you do it on the inside of the tube. And the stationary phase is on the wall of the inside of the fused silica capillary. I'll show you a diagram in a second. Okay, let me go there now. Here's my rendition of what that looks like. This is what we call wall-coated open tubular chromatography in a capillary. And you'll see people use that acronym WCOT. So the basic element of this is silica. So you have a fused silica capillary. The diameter of the ID of the capillary is what matters chromatographically. And you can get these with diameters ranging from about 50 microns on up to about 500 microns. 50 microns is really pretty darn narrow. The inside wall, the lumen of the capillary, is coated. That's what this shaded stuff is. It's coated with a stationary phase. The film thickness in general would run from about 1/10 of a micron on up to 5 microns. Then the outside of the fused silica tube is coated with another polymer, usually a polyamide type material. They're very thermally stable, they're easy to coat, and they add a little bit to the mechanical stability of the system. The terrific things about silica are, fused silica are chemically, it's very, very inert. It doesn't cause decompositions much. It'll only do it when you don't want it to. And it's mechanically very stable. And it's pretty easy to get a film of polymer on it And it's also possible to chemically covalently bond that film of polymer to the silicon, which is also an important characteristic. So we're talking about chromatography inside here. And by the way, if one does capillary electrophoresis, basically you use the same thing, except you don't bother with the stationary phase. But we'll get to that when we do capillary electrophoresis later on. Now, in order to understand this device, we have to understand the physics of flow inside a tube. And we're going to use cylindrical tubes. That helps a little bit. People have solved the problem for rectangular tubes and for hexagonal tubes and whatnot, but nobody who does chromatography could care about that. The fundamental equation of flow in general is an equation known as the Navier-Stokes equation. And the Navier-Stokes equation is nothing more than Newton's second law of motion applied to a fluid. So we're going to talk about viscous flow, and in particular, one particular solution to the problem of viscous flow is what's known as the Hagen-Poiseuille flow equation. This is the fundamental equation of fluids in capillaries. Later on, we're going to get into, as I sort of foreshadowed here, the mass conservation equation in an open tube. And these will lead us ultimately to equations for the HETP inside the tube. Now, in about a day and a half, we're going to get to this equation known as the Aris-Taylor dispersion equation. And this is effectively the broadening coefficient. It's an effective diffusion coefficient or dispersion coefficient when you have Hagen-Poiseuille flow inside of an open tube. What this equation is telling us is that the broadening acts like diffusion. Acts like diffusion. This is a pure diffusion coefficient. This number here is a dispersion coefficient, but it acts like diffusion. But it's diffusion that has a velocity dependence. There's the velocity. We're working on understanding where this comes from, because if we can't understand where this comes from, we will not understand broadening in an open tube. So we won't understand capillary GC or capillary LC. The Golay equation is actually slightly more advanced than the Aris-Taylor equation because it allows there to be retention on the wall of the tube. This equation makes no mention of retention factor because it assumes there's no stationary phase on the wall. Golay solved the same problem, but he said, oh, there's retention on the wall of the tube. Hence, we have these dependencies on the retention factor, and we can then convert this dispersion coefficient into an HETP. So this final equation here is really what we're headed towards. So the idea is we want to understand where does this equation come from, and we will then understand broadening. Now look at this equation. There are no fudge factors in it. There are no adjustable parameters in it. Everything in it is chemically measurable. There's a diffusion coefficient, radius of the tube, there's the velocity, there's no omegas, there's no lambdas, there's no alphas. And this equation works. You can predict the magnitude of the HETP without fitting any data. once you know the diffusion coefficient, the velocity, the retention factor, and the radius of the capillary. So this is what we're trying to get to. But to get here, we have to understand the physics of the flow inside the tube. So that's what we'll start to get into on Friday. I would like those back.
On the table.
Yeah.